Hello, everyone. Another exciting edition of Materials Engineering Notes. Today, we're going to look at creep failures. By the way, these notes are on Canvas, and you can print your own or get them electronically and follow along. So creep. What is creep? Creep is going to be time dependent, usually, let me write a little larger. We're going to say long times. Right? Creep failures can take up to months or even years, depending upon the situation. They can also happen very quickly, but usually we see them in situations where they're stretched out over a long period of time. It is characterized by permanent deformation. So that's going to be strain. Permanent or plastic strain under typically constant load. That's different than a tensile test, okay? This is not like a tensile test. In a tensile test, the load is increased until the failure of the specimen. So this is typically a concern for materials at high temperatures. And again, we're going to put high in quotes. Okay, here's why. For a refractory metal alloy, something really high in, say, cobalt and nickel, like a cobalt nickel, maybe steel, or just a straight up cobalt alloy. For tungsten alloys, high temperatures is easily over 1,000 degrees Fahrenheit. For a lead tin electrical solder, high temperatures is room temperature. So hundreds and hundreds of degrees of differences in what do we call high temperatures. It is going to be based on the melting point of the material. So usually at a greater than about 0.4 of the melting temperature, so 40% or greater of the melting temperature. You need to do that in absolute scale. So not just, oh, we're going to Google the melting temperature of aluminum and find it in Fahrenheit and then multiply it by 0.4. No, it's got to be converted generally into Kelvin is the easiest conversion. So, examples where we are concerned about this: airplane engines, power plants, especially nuclear reactors. So any type of steam generation and handling, very large engines, right? So trains, planes, ships, all that type of engine and combustion. So looking at analyzing or testing creep failures, we're going to have a specimen in a furnace. So here's our heat. We're going to put this under a constant load. and watch how the specimen behaves under that load as heat is applied. So an actual testing setup looks something like this, a little bit of glare to get off. You can actually see they're just weights. Down here, there's a rod that connects up into here, and this is our furnace. So, and then over here's the controller. So it's not the most complicated setup. We're going to hang weights off of a specimen, apply some heat in a furnace, and then we will watch it strain over time. So we will measure strain as a function of time. So if I've got, say, let's flip this over and do a quick drawing. If I'm looking at the cross section of a airplane engine, it could be steam generation, whatever. Let's say I've got some kind of fan blades in here in my awesome jet engine, and they are spinning. If these stretch enough, right, they strain out enough such that the blade connects with the housing and we have an impact, that's bad. We don't like our jet engines to shred themselves in midair. That's generally considered terrible, as in like always. So we would like to know if this is going to creep fail, how long do we have? And if it's going to creep fail, and we know it's going to take, 3 years of at high temperature use, how about we take the blade out and scrap it after a year and a half and give ourselves a 50% factor of safety? Something like that is why we're concerned with creep failures. Now, something else to be noted about this is that this load is usually, don't miss this, less than the yield stress. So I need to emphasize that. At less than the yield stress, we normally expect a material to not fail, right? It should be in the elastic region, and it should not yield, and it should not reach its ultimate stress. But at a higher temperature, over time, the material can still fail. So what's bad about this is a slow creeping, like it. It is a slow creeping failure of the material at high temperatures over time at a stress that can be less than our room temperature yield. Doesn't have to be. If we load our material up near the ultimate tensile strength and then heat it up, it will creep failure very quickly. So that's why I say can be less than the room temperature yield strength. Doesn't have to be. But usually that's when these are insidious and creep up on us, is We do our analysis like good engineers, doing some math and some computer modeling, and we go, oh yeah, this fan blade is great. It won't fail. It doesn't see enough stress. And then it fails. And we go, oh, well, I did my strength and materials analysis or my advanced strengths and my machine design, and I don't know. Well, it's a creep failure. Okay, so this is where materials becomes important. It's all boring until stuff starts breaking and killing people, and then all of a sudden material science is an important thing. And that's more or less true. So that is an alternate definition for creep. That's why we care about it. So what does creep behavior look like if we put it on a graph? Because we're engineers and we like graphs. Here are the stages of creep. We get some instantaneous, almost instantaneous. Nothing is truly instantaneous, but very fast, elastic deformation. Oh, here, let me do this. X-axis down here, if you're having trouble reading it or don't have the slides in front of you, is time. Y-axis is strain. Right, so don't confuse this with a stress-strain graph. Strain is now on the y-axis. Stress isn't here. Stress is just a constant. And then x-axis is time. So what are we doing? We're looking at stretch or strain over time. So initially we get some elastic strain as soon as the stress is applied. So elastic at stress application. That establishes time equals 0. Now we have a stress and the clock starts ticking. We will get primary creep. We will get secondary creep. And then tertiary creep. I'm not going to go into a whole lot of detail on this, but this is a fast region. This is a steady. It's linear. So this here is linear. If I can spell linear, there we go. There's a linear region that's secondary creep, and then tertiary creep again speeds back up. So we get a little bit of elastic beginning deformation. Primary creep starts off fast and then slows down into the linear region of secondary creep, and then as we get close to failure, we speed up in the tertiary region. I have some data for lead tin data from a previous materials lab class where we set up some lead tin solder wire in a lab, added a weight on it, and measured it over time. I've got that data that I'll post on Canvas so you guys can see what this looks like is real data. Okay, so moving on to our next thing. Things that affect the speed at which creep happens. Okay, down here at temperatures less than about 40% of the melting temperature. Again, we've got creep on the y-axis, time on the x-axis. Okay, so this is just schematically looking at the behavior. This isn't real data with real numbers. It's just trying to show the behavior. We may get a little bit of creep to start. Maybe. Maybe not. Okay, but then here, this should go on and not not experience creep failure. Hey, that's a good thing to know. So think this through. If it's less than 40% of the melting temperature, and we generally don't expect a creep failure, more or less, what if we have a part that's failing in creep? What's one way we can resist creep? Well, if it's a function of the melting temperature, what if we take T melt and we increase it? Well, now 40% of T melt goes up because it's just a percentage, right? So we increase melting temperature, then 40% of it also goes up with it, and now we resist creep at higher temperatures. That's a lot of the ways that we resist creep failure, is by trying to increase melting temperature. We'll talk about that some more later. But if we increase the temperature, so here temperature 3 is greater than temperature 2 is greater than temperature 1. Okay, so red line, blue line, green line, right? So we're increasing temperatures, we go this way. Or we could say leaving temperature the same, but as long as we're above 40% of melting and we're increasing the stress. So this is between these three lines, going from this line to this line to this line, we're looking at increasing temperature or stress. So we will have faster creep progression at all stages. So primary, secondary, and tertiary, which means we get faster failures. So like I said on a previous slide, we at a stress that's close to the ultimate or is somewhere past the yield, this goes fast. We can get a fast creep failure. So I've done experiments where I load up lead or tin or lead tin wire. All of those have low melting temperatures. That's why I'm talking about those. Load them up in the lab at a high stress and at room temperature before the end of a 3-hour lab period. We get a creep failure. So we can make this go fast if we want. That's hard to do in something like a tungsten alloy. Okay, so about creep, why is this happening? And how does it happen? The actual physical metallurgy behind creep is reasonably complicated. We're not getting metallurgy degrees. We're not getting material science degrees, and we're not in grad schools. So we're going to kind of water this down to the main reason and call it good. There are different types of creep. So with different mechanisms behind what's happening, but this is the primary one that we're going to go over, that's the most common and the easiest to explain, actually. So we've got some grain boundaries here. So this is a microscope picture of a incomplete, so a partially finished creep failure. Okay, so there's some grain boundaries in here. They're hard to see unless you've got the slides in front of you, but like we can follow along, and they look like very thin cracks in the material. Right, so we've got some in here that these are grain boundaries. Well, along some of the grain boundaries, like here and along here, we have got separation of grain boundaries. So these dark void-looking spots, those are holes in our microstructure where we have cracks and voids. Those occur along the grain boundaries because grain boundaries weaken at high temperatures. And so what literally happens is our grains just come apart from each other. So in our microstructure, okay, there's two grains. Well, remember I've talked about they'll have different crystal orientations, right? So here's my, like, we'll say these are cubes. They've got a certain direction. When we hit the grain boundary, it's going to shift direction randomly. Well, let's just say this is going to go like this. The atoms do bond across grain boundaries. Okay, we get bonds, but they are not in the normal crystal stacking sequences, right? So these are probably still the same crystal structure in the two grains. They're just oriented different. So if I'm following along a certain direction, let's just say I'm going along, I don't know, a 100 direction. Okay, when I get to this crystal, now it shifts. There's an angle. Okay, so we've done that when we've talked about grain boundaries. Those shifts, we still get bonding across the grain boundaries, but it's not quite as good a bond, so to speak, as within the bulk crystal structure from one normal unit cell to another. So at high temperatures, those bonds weaken a lot. So what's going to happen? The grains are going to come apart from each other. That's the start of a creep failure. So, danger of creep. Okay, this slide's filled out for you. I didn't feel like writing all this. So, National Board of Boiler and Pressure Vessel Inspectors. So, that used to be a huge thing in mechanical engineering. It still falls under mechanical engineering. So, talking about in a plain carbon steel alloy. So, that's going to be like a 1018 steel. Right, so 1018, plain carbon steel, low carbon, basically iron carbon alloy. Increasing 60 degrees, specifically from 1040 Fahrenheit to 1100 Fahrenheit, will decrease creep life. That's the life of your part before it fails, specifically in this case, like a pressure vessel, by 90%. So right there is your area where you're crossing that threshold of somewhere around 40%. We're a little over 40% in temperature when we're here for melting temperature. But very specifically right there, we're really crossing a threshold where creep speeds up. So approximate starting temperatures for creep. So these are going to be approximately 40% of the melting temperature. Again, with plain carbon steel, about 800 Fahrenheit. Let's now take that plain carbon steel and add 0.5% of molybdenum. We jump up 50 degrees before we really worry about creep. That's okay. Let's add a little chromium to that. Okay, so now we've added molybdenum, now we're adding chromium. So we've got a different alloy. Now we go up to 950. Well, cool, let's add some more chromium. Let's add more molybdenum. We're up to 1,000 Fahrenheit. Full-blown stainless steel, which in particular we're looking at chromium and probably nickel. Your really cheap stainless steel may only have chromium. Your good quality stainless steel is going to have at least some nickel, if not like up to 5% by weight nickel. So if you ever turn over silverware that's not silver, it's actually stainless steel, on the bottom of it you'll see some numbers, like a 2-digit number, a dash, and a 2-digit number. That should be the amount of chromium and the amount of nickel. I looked at one of the Chinese buffets in Martin one time, for instance, and there was a 10-00. It's 10% chromium, 0% nickel. Nickel is the expensive additive. Real good stainless steel needs nickel, though. Chromium just doesn't add the corrosion resistance on its own. Nickel also has a higher melting point, so it ups the melting point of our steel alloy generally, increases it. So in full-blown stainless steel, something like, literally silverware stainless steel that's maybe a 15.5 or something like that, or a 10.5, you're looking at over 1,000 degrees before we're worried about creep. So that's significant, because we go back up to here, we start to reduce our concern for a rapid creep failure. So let's talk about resisting creep failure. So some way, somehow, I'm going to find a way to test you guys on this. We want to generally resist creep with high melting temperatures. Also, high elastic modulus. I don't think there's an O in that. There we go. Generally, though, if you have a high melting temperature, you end up with a high elastic modulus. And then here's a new thing. Large grain sizes. Okay. Way back when we did the Hall-Petch equation and relationship, you guys remember that? The yield stress is a material constant plus a slope times 1 over square root of the average grain diameter. And remember, we said that smaller grains were stronger. Smaller grains, good. That's what that equation told us. We had a test question on that. Now I'm saying large grain sizes. So back when we did Hall-Petch, I said, this is true at room temperature. And I'll tell you later why. Okay, we're at the why. I said we'd get here. We didn't get here in the classroom, but we got here with me. Yay, talking on the PowerPoint. Okay. So, large grain sizes, or if we go way back to the very beginning of class, single crystals. Okay. So if we can get all the way to single crystals, this is a conventional casting. So our conventional way of melting and solidifying metals with metals casting gives a very polycrystalline structure. So this is great at room temperature compared to a single crystal, but at high temperatures it's not. It reverses. So what do we like? Things that are especially resilient to creep: stainless steels, refractory metals, usually things that are going to have tungsten, right? So W is our periodic symbol for tungsten. But also we have a category that they literally call superalloys. I don't know, it was like the 60s or 70s and the era of comic books, and I guess they just decided to call it superalloys. Okay, those usually have a lot of cobalt and nickel because those are higher melting point materials. Also, don't discount tungsten. So, but also materials that we can make single crystal, which is really a manufacturing process to do this. This requires incredibly slow solidification. So whenever we make metal components, we've got to start with liquid metal and go through some form of metals casting process. In general, we melt metal, we pour it into a mold that's often made of sand, like a fancy sand castle. Once it's solid, we just break the sand off from around it, clean it up, and there's our part. Well, that's a conventional process. In more scientific settings, we can control the heat within a much fancier mold, and like a metal mold that has external heating elements, or internal heating elements actually. And at the top, we can turn those off and start cooling down, say, the top, and then slowly turn down the heat as we go down our part. And we force a single crystal to form up here and then grow its way down. Very expensive. We're talking very high-end commercial or military grade parts right here because of the expense and time involved in making these. As an intermediate, we've got this guy hanging out in the middle, which is columnar grains. If you're able to look at the picture, the part has been treated with an acid on the surface to bring out the grain boundaries. Actually, over here, we can see all these different spots that are different shades of blue and gray. And each of those little blue and gray spots in here is its own grain, which are actually very large grains because we're not using a microscope. Here, a single crystal also means, right, this is a single crystal, or you could say single grain. I don't think that's technically wrong, but people usually say single crystal. Columnar grains is still polycrystalline, but it's got long grains here that run up and down the length of our part. They run all the way up and down. And since we've got very large, long grains, this resists creep a lot better than just your conventional casting, but it's faster and cheaper significantly to make than a single crystal casting. I don't know by how much. I don't think they usually release that information, but I do know that, you know, you're looking at an order of huge increases in cost at each step of the way. Mostly due to the amount of time it takes. This is faster to do. We can cool this down faster. Generally, nature does this. One time in my backyard, I had a bucket of water freeze in columnar grains. So that was real interesting. That must have been a very, very slow um, shift to the freezing temperature in my backyard, and I actually got pictures somewhere of columnar grain water crystals. Anyway, hang on to a mental image of these three, and we're going to paste this on top of it. So this one here, this conventional casting is going to go with this, columnar with this, single crystal with this. It's like hand-drawn pictures out of like Microsoft Paint. What would this look like as a microscope view, right? So now we're in microscopes. Conventional grains, grain boundaries like we've seen outlined here. Now we have long grains. That's our columnar grains. So this is traditional grains. Columnar grains. And then this is a single crystal. There's nothing to see in the microscope because we don't have any grain boundaries to see. Right? So in a conventional light microscope, we wouldn't see anything. It would just be a polished surface. So, and there's our increasing resistance to creep just based on the microstructure. So we can play with the microstructure and we can play with the chemistry to resist creep failure. Here's how we play with the microstructure or adjust the microstructure. I'll show you this slide, by the way. Right? Hey, real microscope pictures based on real turbine blades. So, there we go. But we can also play with the chemistry. We can increase the melting temperature. And that's our two big ways to resist creep failures in situations when we cannot lower the operating temperature. I know at one point, one professor around here that's no longer here, but was looking at trying to resist creep failure and material weakening for power plant structural materials, because like a coal-fired power plant, or actually any power plant, if we can run it hotter, sometimes we can increase the efficiency. Just depends upon the process we're working with. So sometimes we're looking at adjusting temperature up or down based on the material. Sometimes maybe we can take an engine and run it at a lower temperature. We can add better cooling. So we can add fancier versions of radiators or better airflow through a turbine engine or something. Usually we're looking at changing the material either microstructurally or chemically to resist the creep failure, though. Okay, so we have now survived creep failures. And yeah, I think that's it.